Hello and welcome to this video. In this video we're going to be looking at the Young's modulus. Now so far in materials we have defined the density of a material, which we called a specific property as the mass over volume, and we said the density of material is specific to that material itself. That material, no matter how much of it we have, will always have the same density. We then went on to look at springs and we defined Hooke's law. And in Hooke's law, so there should be an apostrophe there, we said that F is equal to K delta L, where K is the spring constant, which again is another value that is a property of the material. Each material will have its own value for the spring constant. We can also go back to electricity. We've looked at resistivity. That's another property, and Young modulus is just another one of these things. So Young modulus is just another property of a material that we can define. Now, in order to define this, density states how closely compact things are. Hooke's law states how hard it is to extend a certain material or make or pull some certain material apart. And Young modulus is very closely related to the spring constant. It is a measure of how strong material is, okay? And it is related to spring constant, and we'll explain that relation in a second. But we first need to define a few terms. So let's first define what is tensile stress. Now, as I pull a piece of wire, so we're going to think of Young modulus in the form of ductile wires for the most part. As I pull along this wire, this cylindrical wire, I'm applying some force in either direction or both directions at the same time. But that force, as I pull it, is actually spread over the total surface area here on both sides, okay? And so my tensile stress is the ratio of the force that I'm applying to the area that I'm applying it across, okay? So this is our first definition of tensile stress. We then have to say that if we were to actually pull this with enough force that we can cause an extension, we can numerically explain what that extension is based on what we call the tensile strain. Now the tensile strain is, let's say this was originally 1 meter long and you pulled it so that it is now 1.2 meters long. The strain is just the change in the length, so in this case it's 0.2 divided by the original length that you had, divided by 1, so in this case your strain is 0.2. Now the units of both of these things are important. The units of stress, we can have actually 2 units, so since it's force divided by area, we can say that's newtons per meter squared, but force per unit area is also the expression for pressure, so we can also relate that to being a single Pascal. And tensile strain, the change in length is a measure of meters, and the original length is also a measure of meters, so we have meters over meters, so actually there are no units of tensile strain. Now from this point we can then relate the Young modulus in, and actually your definition of what the Young modulus is the ratio of tensile stress, which I'm just going to write as stress from now on, divided by the tensile strain. Now these 3 equations that I've put in boxes here are all on your formula sheet, and actually I would recommend learning a specific skill that is going to help you answer these questions. If Young modulus is stress over strain, in order to calculate Young's modulus via this method, you're going to have to first calculate the stress, then calculate the strain, and then take the ratio of both of them. However, that's going to waste a lot of time in an exam. If you can learn this simple trick quickly and be able to do it very rapidly in an exam, it will cut the time down and it will basically make it much quicker for you to answer the questions. So Young's modulus, which I'm just going to note as Y for now, is the stress, which is force over area, divided by the strain, which is the extension over the original length, and this is a fraction divided by a fraction, and when I do the maths behind this, you can prove this for yourself. It becomes F times the length divided by the extension multiplied by the area. So let me get rid of this part and we'll just put this aside here, and I'm going to put it in a double box just to show that it's not on your formula sheet, but I do recommend that you learn this. Now, I wouldn't recommend memorizing anything. I don't recommend memorizing anything in physics. It's probably not a great way to go. Always approach physics with the mindset that you want to understand it so that you can apply it to different situations. If you just memorize stuff, you're not going to get very far in physics. Okay, so now we've defined what the Young modulus is. It is the ratio of stress over strain, which basically means the more force that we put in over some area, we're going to get a larger extension. Now, I'd like to point out again, this Young modulus is a constant property of a single material. If I change the length here, I'm not going to change the Young modulus, okay? This is a constant number. If I change one of these variables, it might change delta L, it might change A, or it might change F. One of these things will change, but it's never going to change Y, because Y is the constant of proportionality between stress and strain. Okay, so if I change any of these variables, I can't change the value of Y. It's a constant because it's a property. Now, from this, how do we measure Young modulus? What do we actually have to do in order to get a value for this? So let's make some space here. So measuring Y. Now this is a required practical, so you will have to do this at some point. But let's rewrite this equation down. So it's FL over A delta L. And in order to measure a value for Y, we need to know these four variables. The very basics of a setup is we're going to set up a clamp stand on a table with some pulley. We're going to end up having some rope that's being pulled with some force. So your force is mg based on whatever this mass is. Your length you can measure with a ruler. Your cross-sectional area, you measure the diameter with a micrometer. So A, measure D with a micrometer. And then calculate your cross-sectional area of a cylinder from the fact that it is a circle. And delta L you're going to measure as you're extending this. So you'll measure the change in length here. Now I'll do this in more detail in a separate video. But what I want to get through here is I can actually relate the Young modulus to the spring constant. Now, what we said for spring constant is that F is equal to K times delta L. Now, we have an F and we have a delta L in this expression as well. So I could rearrange this and get F is equal to Y times A over L times delta L. Okay, and you'd notice that I can actually equate these two. Now, for your A-level physics knowledge, this is not going to be useful to equate these. I'm just doing it here to demonstrate that they're not the same thing. While they are proportional to each other, they aren't identical. Okay. So, where I want to go from here is what we said in the springs video, is that I can make a graph of F against delta L, and I will have a straight line up to some limit of proportionality, and then after that I'd get some extension curve like this. Now this means if I have a very similar property for Y, in order to get the gradient of this is currently K. If I want the gradient of a graph to be Y, my X and Y axis have to be stress and strain. So now to get it into the terms of Young modulus, I have stress on my y-axis and I have strain on my x-axis. And instead of me drawing these different graphs for these different things, I'm actually going to insert a graph in here now that we can look at and analyze from there. So here is my stress against strain graph, and what I'm going to do in this graph is I am going to now demonstrate that for different types of materials that we have, We can always calculate a value for the Young modulus. However, when we get to certain extensions or certain strains and certain stresses, they will all experience different sorts of behavior. Now, stress, we want to make sure on these graphs that we have units. Stress in pascals, I'm going to say. We have three types of materials in this graph. So the first one is a brittle material. Now we can see for brittle materials, we've applied quite a lot of stress for not a lot of strain, okay? That's because brittle materials are things like plates. So you can probably imagine you can put quite a lot of force across them, or you can pull them apart with quite a lot of force, but you're probably not going to get it to extend at all. Now, the reason this cuts off here is this is the breaking stress, okay, or the breaking point. At this point, the brittle material has basically just shattered, right? So if you drop a plate on the floor and it puts some force up against the plate's just going to shatter if the stress is too high. Now for ductile materials, these are the most common types of materials that we will look at. Now ductile at GCSE is sometimes used to define anything that could be made into a wire, hence why for all of these examples so far I have said that we're taking a look at examples which are wires. Now we can define some points. So this point here I can define as my limit of proportionality, the same as it would be in a force against extension graph, proportionality. And the limit of proportionality is just describing the point where stress is no longer proportional to strain. Because you can see after this, instead of having a dead straight line like we do here, we actually have this curvy nonsense over here, okay? Now, this curvy nonsense actually has some interesting behavior. So we're gonna reach this point here, or somewhere around that point, which we're gonna refer to as the yield point. Now the yield point is where after the yield point, I'm going to start having plastic deformation. Okay, so let me get rid of this so we can actually write some definitions down. Okay, so now we first introduced the limit of proportionality. Okay, and this is basically the point where F is no longer proportional to delta L. F is not proportional to delta L, or you could also define it as stress is not proportional to strain. So not proportional. Okay. We then have the yield point. The yield point is where after the yield point, we have plastic deformation begins to occur. Now, what do I mean by plastic deformation? What is that? Well, we have two types of deformation that occur. We have elastic deformation, which is where, if you imagine an elastic band, if I apply some force and I extend it by some amount and I let go, it will go back to the same length, hence it's elastically deformed. So if I let go and I stop applying a force, it will go back to the same original length. Whereas plastic deformation, if you imagine having a box of plastic and you stretch it so it pulls apart, if you let go, it's going to stay in its new position. It's not going to go back to its original shape. And so that's what plastic deformation is. So this is deformation that is like consistent, so it will stay in its new form. So the yield point is the point where above this I'm going to get plastic deformation. Now in terms of the graph, what this means is if I were to let go at some point, so let's say I get to this point and then I stop applying the force, and I have a little curvature here, and then it's going to go back down to the new original length, which I'm going to call L. Okay, so your original length here is basically defined as a 0 point. When you get to here, you're now going to have a new original length. And you'll notice that I've done my best to try and make this gradient the same as this gradient here. Okay, and there is a reason for this. And that's because the gradient of this is actually a property of the material. And we've said before, the gradient here is stress over strain. So the gradient of a stress-strain graph will be the Young's modulus. So let me write that up here. Gradient of stress-strain equals the Young modulus. Now, when we get to this point here is called the maximum breaking stress. So if we were to put any more force on at this point, it would break instantaneously, and you can tell that at this point the force that you apply decreases, even though the strain will continue to increase. And at this point here, it's the same as here. This is the breaking point. This is just where you'll snap the wire, essentially. Okay. Now the plastic deformation at the bottom here will have most of the same points. It definitely has a breaking point here, and it has a limit of proportionality here, which I'm just going to call limit of proportionality, because you can see here it's directly proportional. After this, it begins to curve and flatten off. So the gradient here will be the Young modulus of this material. However, it's only a very small amount of stress that you can actually apply before you get an not consistent proportionality, is what I'm trying to say. So you can only apply a very small amount of stress until you plastically deform. So your yield point would be around here. I'm going to call that YP. This is your yield point. And after that yield point, you have plastic deformation. So you're going to end up, if you released it there, your gradient must be the same as what's here, because it's still the Young's modulus. And you would end up with some new original length around the same there. Okay? So, the things that you have to know about the Young modulus. The first is the equation. So you need to know this equation up here that I'm going to put in a red box. This is probably the most important thing that you need to know, so that you know how to calculate it. You need to know it's a property of a material. Each material will have a different value of the Young modulus, and each value is specific to that material. You then need to know that it's analogous to the spring constant, so it's a measure of how difficult it is to extend something, but you cannot say that they are exactly the same. They will be proportional. Then you can say if you plot a stress against strain graph, the gradient of that graph up to the limit of proportionality is equal to the Young's modulus of that material. And for different materials, you will observe different behaviors on a stress strain graph. Now you will need to be able to recognize the difference between these three materials. So a brittle material, you should be able to spot as being a straight line up to a breaking point. Ductile, you should be able to see as this curvy stuff. And plastic will always have a very low amount of stress applied for a very high amount of strain. Okay, so this concludes the Young modulus, and this also concludes materials. As always, do as many practice questions as you possibly can. If there's anything that's going to help you, it's going to be the practice questions. So keep going at those, and I will see you in the next video.